Awesome. So, Lat, are you ready for the demo? You know,
Yes, sure. Let's present.
cool. So I'm gonna share your screen right now.
Okay, so you will see my screen. I'm connected to 2 instances on Google Cloud. The upper one is where I'll be running Dragonfly. It has an NVMe drive attached to it, which offers very quick read and write performance to disk. And the lower one is just a client instance that we'll be using to connect to our upper instance. And what we'll do first is we'll run Dragonfly. You will see that it started, it runs, and we'll set a memory limit of 28 gigabytes, which is a moderate amount of memory, not quite a big workload. And what we'll do is we use our own utility, which is kind of similar to memtier, to fill up the instance with keys of the size of 1 kilobyte. So we'll set a target rate of 300 requests per second, and it'll take a few dozens of seconds. So we'll be filling up this data store, and while it's filling up, you'll see the logs on the bottom. I'll tell you about the plans. We'll then shut down this instance, but we'll save a snapshot of all the data. And what we'll do next is we'll start an instance, but with smaller memory requirements. And those smaller memory requirements, we'll see that they will allow us to fully import all the data and then run some queries on it. So we'll see it's about halfway through. When we'll be running the queries, we'll analyze what the latencies are and what target number of requests per second we can achieve. So we're almost done with filling the instance.
Awesome. Almost there. It's like yesterday. Sorry. By the way, Dragonfly just hit 25K GitHub stars. So yeah, I think Laura mentioned that. So yeah, basically the marketing team or like many other team members are waiting, are waiting to hit this number last night. So kind of like what we're waiting for, exciting things to happen here as well. So cool. I think it's done now.
Yes, it's done now. We see that our insert failed, and if we query the DB size, we have, oh god, how much? 27 million keys stored inside Dragonfly, and we'll see that it takes up 24 gigabytes of space. So we'll stop the instance. I send an interrupt to it, and it will be saving now all the data. It will take around 25-30 seconds to save those dozens of gigabytes. By the way, what we are actively working on now is to even further improve our snapshotting performance for tiering, so it will more efficiently handle and batch together values.
Right. Yeah. So I remember that Dragonfly now does snapshotting around 1 gig per second. That's already like very fast if you compare with some like Redis snapshotting speed. Yeah, as Lat said, it would be amazing that this can be even faster. I don't know how, but I would be excited to see. Cool.
So what we'll do next is we'll start Dragonfly, and contrary to the previous command, we'll set a memory budget which is half as large, so it'll have twice less memory to accommodate all the values. But what we'll use now is a new SSD tiering feature, and you'll see the flag which is listed last. It's the tiered prefix. It should point to some kind of path in your NVMe file or drive. I'll run it. NVMe file or drive, and there will be, it will create files for every thread. It will create a backing file, which is just used to store data. So we'll see that from the logs, it is loading our snapshot, and let's see, it loaded already around 13 million keys. Then what we'll do is we'll query the memory. And we'll see that our total memory usage, RSS memory, is around 13 gigabytes, which is less than the 14 gigabyte limit that we specified. And you'll see it is still loading. So it turns out that we can fit our huge 25 gigabyte dataset into a smaller memory requirement. You see that it stays still at 13 gigabytes. And it finished. Let's see. It's the same number, 27 million keys. So the last step will be to run some queries. Oh, I forgot. Let's first look at some additional information. So here in our special, we have a new section for info all. I think almost everyone who uses Redis is familiar with it. And the sections, we have a new tiered section, which allows you to view some statistics about the tiered storage. And you can see that we currently store 21 million values on disk. You can see how much memory they take up. So it's, I assume, 18 gigabytes, and some auxiliary stats that we have to closely monitor it. But what we'll do now is we'll use our tool for benchmarking, and we'll run reads with the Zipfian distribution, which kind of mirrors a real workload, and we'll target 300,000 operations per second. And you'll see that we are close to it. We are reaching close speeds. So we can keep up with the required pace. And you'll see that our P99 latency, which is a very strict, like a very upper estimation, is 5 milliseconds. But as we'll see, the average and the mean latency will be much, much lower. It will be lower than 1 millisecond. And Roman, our main tech lead, he actually tweeted about his experiments yesterday, where he compared our new tiering feature with existing solutions which are out there, and he'll show us in all his benchmarks and examples how other solutions fail to provide low latency when reading huge volumes of data and coping with a very, very large number of requests per second. So we've almost run a benchmark. You can see we are running consistently at 300,000 requests per second. And if we scroll up, we see that our median latency is 300 microseconds, and our average is 700. You can see it from the latency graph. So from these numbers, we can conclude that to an external user, there should be almost no visible effect if he runs with tiering. And as there is no visible effect and no latency spikes for him, he will see that he can reduce much of his costs by moving values to the disk. And what our tiering feature also does underneath is it tries to use the existing memory that it has, meaning the RAM memory, as efficiently as possible to accommodate the most frequently accessed keys. So if your workload is even more heavily skewed into accessing only some frequent keys, you will see that your performance won't degrade, won't drop, and you can cut back all your costs, all your RAM requirements, slash them by a factor of 2 or 5, and keep the main values just on disk without sacrificing performance, latency, or throughput.